All right, let's start with problem of the day. This problem of the day was tricky. How many of you guys agreed? Yeah. So one thing you guys will learn with organic chemistry, especially if you're going on to second and third term, is you start to develop a lot of intuition. One reaction looks a lot like another reaction, and that looks a lot like another reaction. So this looks a lot like SN1 reactions where a leaving group falls off, and then what happens after our leaving group falls off? A rearrangement, right? So let's do this, because E1 reactions are remarkably similar to SN1 reactions. So I'm going to write out my sulfuric acid. And the fastest reaction in chemistry is what? Acid-base chemistry. So this alcohol will grab this proton off of sulfuric acid. All right, now we've turned our alcohol into an excellent leaving group. It wasn't a good leaving group before because if hydroxide falls off, it's very unstable, but now if water falls off, water's neutral, it's okay. So we'll draw this water falling off. What do you guys notice about the carbocation that forms? It's secondary, yeah. Secondary carbocations aren't super stable. So what can we do to stabilize this? Methyl shift, right? If I tried to grab one of the protons down here, or I should say hydride and do a shift, we just move it from secondary to secondary. That's not going to increase stability. But if we do a methyl shift, we will increase stability. So one thing I'll try to pound into your guys' head is anytime you can form a more stable carbocation through rearrangement, it will occur spontaneously. It won't occur spontaneously to a less stable carbocation. So always try to find the more stable product that can form. So this is a 1,2 methyl shift. And we're on our way. Now we've made progress. We've got a tertiary carbocation. All right, tertiary carbocations, we agree, are a lot more stable than secondary carbocations. But what can stabilize a tertiary carbocation even more? Resonance. So maybe there's another rearrangement we can do. So a tandem set of rearrangements. Whoops. So let's think about this. We've got another hydride over here. So I'm going to draw this hydride hopping over to that adjacent carbon. So this is our 1,2 hydride shift. And we're almost there. Now we've got a tertiary carbocation again. So let's label this. But this time we've got resonance. All right, so let's consider the other resonance structure. And I want you guys to stop me if I'm doing something wrong. All right. Oh, whoa, what happened? Can't move a positive charge. This is something I see often on organic exams as people get tempted to move the positive charge around. Remember, you can only show electron pushing of electrons, not a positive charge. So let's move this pi bond over. So we're almost there. And am I done with my resonance structure? No, we have a positive charge over here because that carbon doesn't have a hydrogen on it. All right. So now, if we look at our carbocation on the left, That looks pretty similar to our product. We've got the double bond in the right location, so we're on the right track. Now what we need to do is identify our alpha and beta positions. The alpha position is either the one with your leaving group or the one with the positive charge. So now our alpha position is at this carbon with the positive charge. Do we have beta protons? Yes. We've got beta protons here, and we've got beta protons here. Does it matter which one we select?
Yes.
No, not really. Because if you think about it, these are equivalent. They're in the same chemical environment, and the sigma bond can rotate, so even if we do form the double bond on the other side, it'll spin around openly in space. So you can really grab either set of protons. And in this case, water can act as a weak base, the water we ejected off in that first step or second step. So we're going to show this as our weak base, grabbing a beta proton. Then this beta proton's electrons get dumped down and will form our new alkene.
You should put
This exact problem on the exam. That wouldn't be much fun. All right. If you want a challenge problem, I told you guys that I wanted you to find the mechanism going to this product. There are two other products, and see if you can maybe identify what the other two potential products are for this reaction. It's an excellent challenge problem, and if you guys want to really understand rearrangements, I would encourage you to figure that out. Yep.
Will you put the answer up?
Yeah. Do you guys want me to tomorrow or over the weekend?
Whenever you
All right. I'll do it tomorrow, probably later in the afternoon. And other questions? Yep.
So when we use the H2O, is it okay if we use the HSO4?
Yeah, so you could have the conjugate base of your sulfuric acid do that deprotonation. Water is a better base, but if you draw any generic base doing that deprotonation, I'm okay with it. Yeah. The reality is in equilibrium, water will outcompete it more, but if you draw a reasonable arrow pushing scheme, I'm more than okay with that.
And for the first two steps, is it okay if we just put in one step?
You should try to draw the first step as two steps, so protonation as a separate step as your leaving group falling off. So try to break things apart into their individual arrow pushing. Just like we did when we first started covering arrow pushing, it gets really confusing if you showed too many steps in one sequence. Yeah, Ramon?
So for the methyl shifts and the hydride shifts, is that numbering generic, or is it just because of how many?
So you mean why do we call it a 1,2 methyl shift as opposed to a 1,3? Exactly. So we can only shift a hydride or an alkyl group from an adjacent carbon. So the 1,2 just means it's one carbon over. Yeah, it's kind of a generic numbering scheme. If it were 1,3, that would mean you're pulling a methyl group from 2 carbons over, and that just doesn't occur. It's improbable. Yep.
But if it doesn't occur, why do we have to distinguish between them?
If you call it a methyl shift, I'm more than okay with that, yeah. Yep.
So, besides knowing the pKa value difference between water and the hydrogen sulfate ion, is there a way to know that water outcompetes a negatively charged?
Without knowing the pKa values, it'd be very challenging, which is why I'm not going to be a huge stickler on what base you use. Yeah. Any other questions? Elijah?
So, like the earlier comment saying, like, can I just call it a methyl shift? Isn't the reason it's called 1,2 methyl shift because we're moving from like carbon 1 to carbon 2?
Yeah, exactly. So,
But if it was specified differently, like we already had like a numbering system set in place, like say just like as a problem, we would have to specify 3 to 4 or something like that.
yeah, by definition, people just refer to it as a 1,2 methyl shift to imply that it's adjacent carbons. People don't typically say a 3,4 methyl shift, for example. Yeah. Yep, Caitlin?
Would it be incorrect if after you form the third degree carbon if your base took that proton and formed a carbon?
No, and that's where the challenge problem comes in. So if you see on the resonance structure on the right, Do we have beta protons? We might have beta protons in other locations that might lead to other products. So that's a part of the challenge problem, and I'll let you guys work on that. All right, let's go back to E2 reactions. And I know yesterday people were starting to get that glazed over look of being completely overwhelmed. I want you guys to know that this is fairly normal for organic chemistry. It's challenging. And I know that doesn't make you feel better, but the goal is I don't want you guys to freak out, get overwhelmed, and give up. The point is we have to learn the basic mechanistic details, and then what we're going to do is go through practice problems. Once you see these in the context of a bunch of examples, you'll start to develop an instinct. So don't give up. Don't get too hard on yourself. Just try to understand the basic trends and mechanisms. So let's go through and do an E2 reaction summary. And I want to nail down some key points that we went over yesterday, and then we're going to see some practice problems. So key points. What sort of base do we need for an E2 reaction? Do we need a strong base or a weak base? Strong base. So must use a strong base. Without a strong base, an E2 reaction simply won't occur. You might have an E1 reaction, like we saw in our problem of the day, but you need a strong base for an E2 reaction. All right, number 2. What was the main thing about our beta protons? They must be anti-coplanars. So key point number 2 is we must deprotonate anti-coplanar beta protons. There were a couple of tricks for identifying anti-coplanar beta protons. Trick number 1, draw a Newman projection. You can rotate it until you find that anti-coplanar beta proton. Trick number 2 is physically build a model kit and rotate it until you find a proton that's anti-coplanar. Oftentimes it's hard to see using a two-dimensional wedge and dash drawing.
Is it true that on a ring it has to be in an axial position?
Your leaving group and your anti-coplanar beta proton must be axial in a chair conformation for cyclohexane. Yeah, that was one key point with cyclohexanes in particular. All right, number 3 was kind of where we ended yesterday. We said if there are multiple beta protons, we have a lot of considerations. So if we have multiple beta protons that, can be anti-coplanar, you must consider stereochemistry and regiochemistry. And regiochemistry. And so let's take an example where we need to consider stereochemistry. So let's do this example. All right, so let me give you an example substrate, and I want you guys to help me predict the different products that we might get out of this reaction. So I've got a tert-butyl group here, a bromine coming off of this carbon, and then an ethyl group over here. And in this case, I'm just going to use a generic base B-. What product or products might we get out? Do we have more than one beta proton? So let's take a look. This is our alpha position. Alpha position is where the leaving group is attached. We do have two beta protons, right here and right here. All right? On the other carbon, with the terbutyl group, there are no beta protons. They're all occupied by a carbon-carbon bond. All right, so we might get two products because we have two different available beta protons. So what products might we get? Sarah?
Is only one of those going to be anti-coplanar?
Yeah, but remember, we can actually rotate a sigma bond so that either of those two protons I've got shown could be anti-coplanar.
You'll get the trans.
Cis and trans, exactly. Okay, so depending on what proton we pick, we could get this alkene. Is that cis or trans? Trans, because the hydrogens are on opposite sides. Or we could get the terbutyl group coming off the same side as the methyl group, and we call that cis. All right, now we have to assess which one's going to be our major product. Is it going to be trans or is it going to be cis? Trans. So we'll call this major. We'll call this minor. So in this case, why is the trans product more stable? Yeah, we have to think about the size of our substituents, right? We don't want that terbutyl group running into that methyl group, because if we do, there's this steric clash that occurs there. That's really destabilizing. And if you try to do the Newman projection and align that proton, you get a really bad Gauss conformation. So this isn't the major product. You may observe a little bit, but it's hard to predict the exact percentages. We just know one's major, one's minor. Yeah?
It can just flip to cis.
Nope, the double bond is locked. But as we saw yesterday, I'm going to flip back in the notes. I'll go back. But you remember example 2 yesterday? I had a similar example where I said we could pick the green proton or the blue proton. And with one of our Newman projections, we can see we've got the blue proton anti to the bromine. And in the other Newman projection, we've got the green proton anti to the bromine. So when we do this, we can see the Newman conformation on the right has that Gauss interaction that is destabilizing. That means we're not going to get very much of the product where the green proton's deprotonated. We will get more where the blue proton's deprotonated, because that's a more stable Newman projection. All right, so we will get a mixture of trans and cis. What's the relationship between these two products? Are they enantiomers, diastereomers, constitutional isomers? Diastereomers. Because if we look at them, the double bond is still in the same relative position, right? But they're not mirror images of one another. Constitutional isomers would have to have completely different connectivity. So typically cis and trans isomers are going to be considered diastereomers. Yep.
So when you drew the cis, is it because you get the protons from the bottom?
Yeah, so when we're referring to cis, we have to find groups that are on the same side. So you see how those two hydrogens are on the same side? That means they're cis.
No, the question is, did you attack the hydrogen from that part, or?
Yeah, so in this case, we could have the beta or the base attack this proton, clamp down, or we could conversely have it attack this proton, clamp down, and kick off our leaving group. So we have two possible beta protons. When we have that competition between two possible beta protons, that means we'll get a cis and a trans mixture. We normally observe trans as being the major product. Okay. Yeah. All right, so if we're forming one stereoisomer in a higher percentage, do we call that a stereospecific reaction or a stereoselective reaction? Stereoselective. Selective means you prefer one, but you don't absolutely get that exclusively. So let's make a brief note regarding stereochemistry. So stereospecific means only one product. Stereoselective means that we'll get an unequal mix of stereoisomers. So in the above reaction that we've got shown, we're drawing a stereoselective reaction because we're not exclusively getting one product. We're getting a mixture of diastereomers. Yep.
For the stereoselective, is it possible that we have the equal ratio for both products?
No, stereoselective implies that there's an unequal ratio.
So will we have an equal ratio filter?
Well, there's no term for the equal ratio.
So there's no way this reaction will form an equal ratio product?
It'd be an extraordinary coincidence. Yeah. All right, so now let's look at regiochemistry, because that was the other side of the coin we have to consider. And with regiochemistry, we're, what's that?
What does G stand for?
What does EG?
Yeah.
Oh, that's a good question. EG, if you ever see that in an English paper or in a book, it stands for exempla grata, which is Latin for example. Or, does anybody speak Latin? It might mean something more different than that. But EG just means for example.
General question, should we speak like
Should you speak Latin? Are you going to be a priest?
I don't know.
Well, if you want to keep that door open, you might want to learn Latin. All right. So let's look at regiochemistry with this product. All right. Let's identify beta protons. Where are there beta protons on this molecule? Yeah, to the left and to the right. So we got alpha position here. And then that means we've got some beta protons. I'll draw the beta protons in blue. So we've got 2 beta protons there. And then we've got 3 beta protons over there. Okay, so now we're going to be picky. In this case, I'm going to use a small base. So I'm going to call this B minus, and I'm going to say small base. Which protons are going to be more accessible? The ones on the right or the ones on the left? The ones on the left are more accessible, but if you're a small base, do you really care? No, you can sneak in and grab either set of protons. So in this case, a small base is going to prefer to attack the more substituted set of protons, or the ones that are more crowded. And this will clamp down and eject off our bromine. So if we look at our final product here, we're going to get our trans product, and then what else might we get that we just saw? Yeah, we might get some of our cis product. Okay, which one's going to be major? Trans is going to be major. But we said the base could alternately grab the other set of protons too. It will kind of indiscriminately go after protons because it's so small. So let me draw this with a different arrow. I'll say, all right, let's say an alternate product could be grabbing these protons, clamping down, and then we kick off our bromine. What would our new product look like if we did the green arrow path instead of one of the red arrows? Well, we have a double bond on the end. Would this be classified as cis or trans, or neither? Neither. Okay, so now we're getting into a little bit about regiochemistry, and I'm going to call this my minor product too, because we said a base prefers, when it's small, to go after the protons coming off of the more substituted carbon. Yep.
Why is that?
Yeah, that's a good question. So let's consider this. I'm going to redraw this a little bit. Let me clean this up. So we've got BR Let me just draw one proton to make our scheme clear. So in this case, we said our base is going to come, grab this proton, clamp down, kick off our bromine. So let's draw our transition state. Our bromine's halfway off. We're halfway to a pi bond, so I'm going to draw that as a dash. Our hydrogen is halfway removed and halfway bonded to the base. So our base is going to be delta negative. And then we've got a methyl group there. And if you think about this, we're going through a transition state where this carbon is losing its proton. So this carbon is going to be delta positive. How can we stabilize positive centers? Think about a carbocation. What can stabilize a carbocation? There's two things. Resonance, I heard in the back. And then the other thing was... Yeah, how many substituents do we have coming off of it, right? So if we look at this one, we can say, all right, this carbon is secondary. So that's got some hyperconjugation stabilizing that positive charge. Let's do the alternate. So the alternate said, well, what if we grab one of these protons? Oop. So I'll draw this going after that proton, kicking off our leaving group. So now we've got base up here. This hydrogen's halfway bonded. This carbon's got a half pi bond. Our bromine's falling off. So this is partial negative. Our base is partial negative. And then this hydrogen over here is partial positive. If we look at where that partial positive is located, is that carbon primary, secondary, tertiary? Primary. So this one is the more stable transition state for small bases. Simply because it's on the more substituted carbon. So small bases always prefer to pull off protons off of that more substituted carbon because it's got that lower activation energy it has to overcome. All right, so let's go back up for a second and take a look at those products again.
Did you say it wasn't trans?
For the minor product in green. Can we classify that as cis or trans?
It has the two hydrogens.
It has two hydrogens, but then the question arises, okay, these two hydrogens are on the same side, but those two hydrogens are on the opposite side, so we can't really classify it as cis or trans. Monosubstituted alkenes, we don't really call E or Z or cis or trans. Okay. Does anybody remember the name of the two products in red, the major and minor products? What were those called? The Zaitsev products. And we said that these are our thermodynamic products. And then the green product, which is our less substituted alkene, is going to be which? Hoffman. Hoffman product. And it's not a thermodynamic product, it's what? Kinetic product. So in this case, when we use a small base, we always favor formation of our Zaitsev products, meaning we're going to get the more substituted alkene as our product, but we may even get a mixture of cis and trans alkenes depending on the situation. All right, let's look at our other example. I'm going to box this, that way it doesn't get confused. Let's say this time we're going to use a big, old, bulky base. So we've got base, this time it's giant, and it's bulky base. We said we've got a bunch of protons, but this time it's going to have a hard time going after these protons off of that secondary carbon. They're crowded. It's closer to the center of the molecule. It's not on the periphery. So in this case, it would prefer to go after one of these beta protons simply because they're more accessible.
How about the other edge?
So the protons coming off of that carbon,
No, the other one.
which one? Off of, whoop, right here? So those wouldn't be beta. We have to look for beta protons. So in this case, we'll say these are more accessible beta protons because it's primary carbon. These protons are less accessible because it's a secondary carbon. Okay, so we could draw them in if we really want, but we know that the proton that's really, or the base that's really bulky will have a hard time reaching over there. So this base will come grab the more accessible beta proton, we'll clamp down, and then kick off our leaving group. So in this case, this would be our major product. And was this Hoffman or Zaitsev? Hoffman. So this is our major product. We would call this our Hoffman product. And it's also our kinetic product. Whoop, shoot. All right, let's go back.
I think you put an extra methyl on there.
Oh, thank you. Sorry about that. Good job, guys. This is why I keep you guys around. Major product, Hoffman product, and it's our kinetic product. Are we only going to get one product out of this, or do you think we might get a little bit of some other products? We get a little bit of some of the Zaitsev products, just like we saw a little bit of the Hoffman products in the previous example. So these reactions aren't super clean. We could get a little bit of our trans product, plus a little bit of the cis product that we saw previously. And we said that these would be our minor products, and they'd be our Zaitsev products and our thermodynamic product. All right. So in this reaction, what's the relationship between these two? Yeah, they're constitutional isomers. You see how the double bond on the one on the left is between carbon 1 and 2, and the carbon-carbon double bond on the one on the right is between 2 and 3. That means we've got a different connectivity. These are going to be constitutional isomers. So in this case, we're dealing with regioselectivity. Oops. So let's make a note about regioselectivity. Regioselectivity is an unequal mix of constitutional isomers. So in this case, we're going to get a major product that is our monosubstituted alkene, and we'll get some minor products that are our disubstituted alkene. So we have to deal with stereospecific reactions, stereoselective reactions, and then regioselective reactions. Those are our main three classes of reactivity with these E2 reactions. All right, do you guys want to see some practice problems? All right. Practice problems. I think these were some pulled off of an old exam. So this gives you an idea what you might expect on the first exam. Or, I mean, this next exam. All right, so that's problem number 1. And I want you to list the product or products if there's multiple products. And if there are multiple products, make sure you label them as major or minor. Then the next one I have
Is it sodium, oxygen, ethanol?
Yep, that's an ethyl. All right, so this kind of puts the reaction in context. If we're looking at sodium ethoxide, would you consider that to be a big base, very bulky, or not so much? Yeah, sodium ethoxide is considered a small base. Do small bases prefer one sort of reaction? Yeah, they typically prefer to form your Zaitsev product. And your Zaitsev product, we said, is going to be your more substituted alkene, so that's a clue. Then the bottom one, we've got a super bulky base. We said super bulky bases can only reach the most accessible protons, so we tend to get the less substituted alkene product. So I'll give you guys a minute to work on this, and then check with your neighbors and see if you guys are agreeing. Always remember to find beta protons. You guys are super quiet. You're more than welcome to talk with your neighbor about this. So we've got strong bases in these. So these are examples of E2 reactivity. Anytime you see a strong base, it screams E2. Weak bases might favor E1. I'll also give you guys another hint. What does sodium do in this reaction? Nothing. Sodium is a spectator. We can't buy a bottle full of anions only. They always come as a salt. So really, the sodium is just hanging out on its own, not doing much in both of these. It's just there to counteract that negative charge off of that oxygen. It is not covalently bonded. It will not form covalent bonds. Raise your hand if you think you've got the first one at least. All right, let's go through the first one. First thing we got to do is identify beta protons. Do we have beta protons over here? No. We have all carbon-carbon bonds, no protons. We've got beta protons coming off of here, so we could grab one of those. Is that it? No, we've got beta protons over here. So again, we're going to deal with the mixture of products. So let's do this with two different arrows. I'm going to go after these red protons, clamp down, kick off our leaving group. That would give us a double bond. Are we going to ever run into the other diastereomer here? With a small ring, remember how I said you really can't run into diastereomers with cyclohexenes? You can once you get to cyclooctenes or bigger, but with small rings, we're stuck with one product. Okay, let's do the other beta protons. We're going to grab one of these, clamp down, and kick off our chlorine. So we'd end up with the double bond right there, and then our two methyl groups. Which one should be major, the one on the right or the one on the left? Left. So this would be major. This would be minor. Is the one on the left our Zaitsev product or our Hoffman? Zaitsev. So the major product with small bases will be our more substituted alkene. And this would be our minor product, which is our Hoffman or our less substituted alkene. All right, let's do reaction number 2. Using the same logic, we have to identify beta protons. So we still have these beta protons up here. Then I've got beta protons here and here. Does it really matter which of these two sets I use? No, they're equivalent. They're in that same chemical environment. But let's do the same thing. Let's do 2 sets of arrow pushing. So I'll grab this proton, clamp down, kick off our leaving group. So if we draw the product for this reaction, we could get that. All right, and then alternately, we could grab one of these beta protons, clamp down, and kick off our leaving group. So we'd get a mixture of 2 different products because we've got 2 different types of beta protons. Which one's going to be major, the one on the right or the one on the left? The one on the right. Why the one on the right? Yeah, the one on the right, if we look at it, is a di-substituted alkene. The one on the left is tri-substituted. The big bulky bases tend to favor the less substituted alkene. So in this case, this would be our major or Hoffman product. And this would be our minor or Zaitsev product. Oh, shoot. I write too fast. So sorry, minor, major, Hoffman, and Zaitsev. All right, do you guys want to see another couple challenging problems? Yes. All right, let's do some that are a little bit trickier. And I'll give you a hint. Remember chair conformations. We haven't used them in a while, I know. And in this case, I'm going to use sodium ethoxide. So a relatively small base, but remember your chair conformation. I'll give you guys another hint too. In the chair conformation, should the bromine be axial or equatorial? Axial. Remember, for an E2 elimination to occur in the chair structure of a cyclohexane, your leaving group must be axial. So let's draw this chair structure. All right, so we've got, let's see, a CH3 group pointing up here. I'm going to draw the bromine sticking down in the back. All right, so that looks good. We've got our trans cyclohexane, our bromine's axial. We have to identify a beta proton that is anticoplanar. Where would this anticoplanar beta proton be? Let's play a game. Yell at me when I'm hitting the anticoplanar beta proton. Ah, there we go. So let's draw this in. This proton is anti-coplanar to that bromine. What about this proton over here? It's beta, but it's not anti-coplanar, so we can't use that one. Let's just erase it to avoid confusion. All right, so now we've got sodium ethoxide, so I'm going to write OET minus. This will come grab our anti-coplanar beta proton, clamp down, kick off our leaving group. And if we look at this, our methyl group stereochemistry went untouched, so that will still be a wedge. And then we formed a new bond right there. Are we going to get any other products? No. So would we call this stereospecific, stereoselective, or regioselective? Stereospecific.
If you left it at 2 dimensions and drew your H leaving as a wedge, that would still be right.
Your H leaving as a wedge? Oh, yeah, that would be fine. Yep.
So there's only one product here because there's only one anticoplanar beta proton.
Exactly. If you only have one anticoplanar beta proton, the reaction by definition is going to be specific or stereospecific. All right, let's do another one. Looks very similar. So let's do CH3, then Br, then sodium ethoxide, and heat. And again, we've got to be worried about chair structures, so I'll get you started with the chair structure. Okay, in this one I'm going to put my methyl group right here. Our bromine should be cis to it, so I'm going to draw the bromine axial, which is perfect because we need our leaving group to be axial. And we have to identify our beta protons. Do we have just one beta proton? No, we actually have 2. So in this case, we can say, all right, we've got 2 different beta protons. This is coming off of a tertiary carbon. This is coming off of a secondary carbon. With small bases, are we going to go after the more accessible secondary carbon, or do we really not care and we prefer to go after the tertiary carbon? Tertiary. So let's think about this, and I'm going to draw 2 different reaction arrows to represent our 2 different products. We could have reaction 1 where we said this is going to be our major reaction pathway where we kick off our bromine. And this would give you your double bond here, and your methyl group loses stereochemistry since it's planar. And this would be, we said, our major or Zaitsev. And then if we did a separate reaction, we could theoretically have a minor product where we go after the more accessible protons, clamp down, and kick off our leaving group. And now we get the same product that we got before. And we said this would be our minor Hoffman product. Is this reaction stereospecific, stereoselective, or regioselective? Regioselective. We're getting a mixture of constitutional isomers out of this reaction. We're not getting a mixture of stereoisomers, so we would call this a regioselective reaction. All right, I think that's where we're going to hold off today. Remember that Monday's review, so try to get a lot of studying done this weekend. If you guys have questions, feel free to email me or stop by my office and I can help you guys. Yeah?
The practice exam, can you get that on Monday?
It's posted on the class website. Go to the class handouts. I posted it on there just to save some paper because some people like it digitally. Just 1 second.
Okay.